We will not create any field output requests, however, we will create history output requests. Right-click on HOutput1 and choose Rename. Set the name to Displacement Output 1. Double-click on Displacement Output 1 to get the Edit History Output Request window. Change the domain to set and choose Displacement Point Set1 as the set. For the output variables, select UT, which is translations. Similarly, create a history output request displacement output 2 for the set displacement point set 2. Now come the boundary conditions. Create one called fix top layer end. It is active from the initial step. Fix one end of the top layer using an Incastor boundary condition. Similarly, create fix core layer end and fix bottom layer end. Let's create the load. We'll call it Uniform Applied Pressure. Activate it in the Apply Load step and set it to type Pressure. We shall apply it on the top surface of the top layer and give it a magnitude of 10 newtons per meter squared. At this point, we should identify and name the surfaces that will be tied together so that it will be easier to create the tie constraint. Let's create some surfaces. Expand the assembly container in the model tree and double-click Surfaces. Name the surface Top Layer Bottom Surf. It is hard to select the bottom of the top layer in the viewport since the core is underneath it. One way to make it visible might be to temporarily suppress the face-to-face constraints between the rectangular block and the plank. A better way is to use the Display Group toolbar, as we did a little earlier, to hide everything under the top layer. Similarly, define the surfaces bottom layer top surface, core layer bottom surface, and core layer top surf. We shall now define the tie constraints. Double-click Constraints in the model tree. In the Create Constraint dialog box, name it Tie Constraint 1 and choose Tie as the type. For the master type, choose Surface. The surface can be selected in the viewport, but we have already defined surfaces in the previous step, so click the Surfaces button. We will set Core Layer Top Surf as the master surface. Check Highlight Selections in Viewport to ensure that we are picking the correct surface. For the slave type, once again choose Surface. Set Top Layer Bottom Surf as the surface. The Edit Constraint window is displayed. Here you can see the selected master and slave surfaces and switch them if desired. Just as in the case of contact interactions, tie constraints can be surface to surface or node to surface. The internal formulations, as well as the advantages and disadvantages of these two discretization methods, were discussed in the contact modeling tutorial, and the same principles apply here as well, with a few minor differences. To refresh your memory, a surface-to-surface approach enforces constraints in an average sense over a finite region rather than at discrete points, and multiple master nodes are used. The surface-to-surface tie constraint differs from the surface-to-surface contact in that each surface-based tie constraint involves only one slave node, whereas contact involves multiple slave nodes. As with contact, the surface-to-surface formulation results in a more uniform distribution of pressure and less stress noise at the tied interfaces compared to node-to-surface. The disadvantage is that it's not as efficient as node-to-surface. Node-to-surface, on the other hand, is more efficient. However, the forces will tend to concentrate at the nodes, leading to spikes and valleys in the stress distribution. The discretization method combo box gives you three options: Analysis Default, Node-to-Surface, and Surface-to-Surface. Analysis Default will use the default discretization method for the solver, which is Surface-to-Surface for Abaqus Standard, and Node-to-Surface for Abaqus Explicit. The position tolerance determines whether or not individual nodes of the surfaces get tied together or not. If the slave and master surfaces are close enough, meaning that the distance between them is less than the tolerance, the nodes will be tied and will remain tied for the rest of the simulation. We shall use the computed default position tolerance here, but you have the option to specify a tolerance manually. Adjust slave surface initial position tells Abaqus to move all the nodes of the slave surface onto the master surface in the initial configuration before running the simulation. This ensures that all the surface nodes are tied. Otherwise, if the gap between them exceeds the position tolerance, these nodes will not be tied, and this may cause some inaccuracies. We shall leave this option checked. Tie constraints always constrain the translational degrees of freedom of the nodes of the tied surface to be the same. However, the analyst has the option of specifying whether or not the rotational degrees of freedom should also be tied. We shall leave this option checked as well. Similarly, create tie constraint 2 to tie the top surface of the bottom layer with the bottom surface of the core. Let's mesh the parts. All three layers should be meshed with 8-node linear brick elements with reduced integration. The approximate global seed size should be set to 0.04. create a job called sandwich structure job and run it. View the results of the simulation. When you try to plot the deformed shape, there does not appear to be any deformation. This is because nonlinear geometry was specified when defining the step, and when NLGeom is used, Abaqus automatically sets the deformation scale factor to 1. Since we use a very small pressure load on a steel structure, there is little visible deformation. We will need to set a very large deformation factor to see anything. Click the Common Options tool. Set the deformation scale factor to a uniform value of 1 million. You will now be able to see the deformation when you view the deformed shape. We will now save the XY data and report it. Expand sandwich structure job.odb in the output database tree. Expand history output. We want the U2 displacements of the bottom layer and core layer at the nodes we have defined using sets. Right-click on each of them and choose Save As. Name them Sandwich XY Data 1 and Sandwich XY Data 2. Go to the Report menu and choose XY. Choose Sandwich XY Data 1 in the XY Data tab. In the Setup tab next to File Name, click Select. Create a folder called Sandwich located in the C drive and store the report in it as sandwichxydata.txt. Uncheck Append to File so that if the file already exists, it will be overwritten rather than appended to. In the Data section, choose to report the column totals and column min-max as well. Repeat the process for Sandwich XY Data 2 as well, but this time check Append to File, so both datasets will be reported in the same file. Using Windows Explorer, navigate the Sandwich folder in the C drive and view the contents of sandwichxydata.txt. You see that the nodal displacement history for the two sets has been written to the report.